Hello, good morning students. Today we will study next point from this chapter. Amines is basicity of amines. We know amines are basic in nature, and in ammonia and all amines this nitrogen have lone pair of electrons, and these lone pair of electrons can be donated, can be shared with electron deficient species, and therefore amines are basic in nature. For example, here trimethylamine share its lone pair of electrons with electron deficient boron trifluoride, and the equation is Me3N means trimethylamine, it is a tertiary amine. Here this nitrogen have lone pair of electrons, and this BF3 is an example of electrophile. So it have capacity to attract the electron pair, and this trimethylamine have tendency to donate electron pair, and the bond is formed between nitrogen and boron. This nitrogen possesses positive charge because of the 4 bonds, and boron possesses negative charge. So this basic strength of amines can be expressed quantitatively in terms of Kb, that is the dissociation constant of base, or its pKb value. If Kb value is a large, then amines are more basic or stronger base, and if exactly opposite to this pKb value, this pKb value is a low, then amines are more stronger. So on the basis of Kb or pKb value, we can decide the strength of bases. So in terms of Lowry-Bronsted theory, this basic nature of amines can be explained by writing an equilibrium reaction. This is amine containing nitrogen with 3 bonds. When H2O is added, then reversible reaction take place. This nitrogen get bonded with hydrogen with the help of this lone pair sharing, and the side product is OH minus. Here the amine containing hydrogen, that is nitrogen, is bonded to 4 bonds. It is positively charged, and it is a conjugate acid. So according to this Lowry-Bronsted concept, this amine accept proton, and therefore proton acceptor is a base, hence amines are basic according to Lowry-Bronsted theory. In this equilibrium, amine accept H plus ion, hence amine is a Lowry-Bronsted base. Stronger base, this equilibrium shift towards right, thereby the Kb value is larger and pKb value is smaller, and vice versa. We will study some examples given for this values of Kb and pKb values for different amines. Here in this table, the values of pKb are given. We know smaller is the pKb value, then more will be the stronger base. First, we will study examples of primary amines. So here first example given is methanamine. Here methanamine, the molecular formula is CH3NH2. So this methanamine have pKb value 3.38. Next is ethanamine. Its pKb value is 3.29. So smaller is the value, more is the stronger base. Here if we compare this methylamine methanamine and ethanamine. Here in ethanamine, alkyl group is larger, which donates more electron. Hence, the lone pair of electron on nitrogen is easily available in ethanamine than in methanamine. Hence, ethanamine is stronger base because of the smaller value of this pKb. The next example is it is propan 2 amine, and one more example is phenyl methanamine. Here the values are pKb values are 3.40 and 4.70. Here the bulky amine group in propan 2 amine that affects the basicity of amine, and hence it is a less basic than ethanamine. Similarly, aromatic ring is electron accepting, it do not donate the electron, hence it is again weak base than these aliphatic amines. Then secondary amine, first example is dimethylamine. This dimethylamine have value 3.27 pKb value. It is a more basic than this any primary amine. Then one more example is N-ethyl ethanamine, that is diethylamine. It is having value, pKb value is 3. It is again stronger base. Then tertiary amine, this values of pKb, they are more than that of the primary amine or the secondary amine, because this tertiary amine have the steric hindrance, and hence they do not lone pair easily, hence they are less basic than primary or secondary amines. Then here the example of ammonia is taken. Its value is 4.75. It is having no electron donating group, hence it is less basic than primary or secondary or tertiary amines. Then aryl amines, we know already that this aromatic ring, which is not electron donating, but it accepts the electron, and hence these are very weak bases than aliphatic any primary, secondary or tertiary amines. So we had studied this comparative study of basicity of amines. Now we will study this basic strength of aliphatic amines first, and then we will study the basic strength of aromatic amine. This pKb values we had now studied from the table 13.4, and the basic strength of primary, secondary and tertiary amines and that of NH3 can be represented in the order like this pKb values. So it is greatest value for NH3, means it is the weakest base. Then next is this primary amine, then secondary amine, and which is less than this tertiary amine have greater value for this pKb than the secondary amine. So this is order of values of pKb for different amines and ammonia, and therefore on the basis of this, the basic strength of amines is here the tertiary amine is a more basic than primary, than tertiary, than NH3. So this is order of basicity on the basis of this pKb values. So aliphatic amines, secondary amines are the strongest bases. Remember this sentence well. In aliphatic amine, the secondary amines are strongest bases. Then basic strength increases as we move from this NH3 to RNH2, that is ammonia to primary amine, and from this primary amine to secondary amine. But basic strength decreases as we move from secondary amine to tertiary amine. So the basic strength and the corresponding pK value, that depends upon the position of equilibrium, and this equilibrium equation that we will study as a equation number 13.1. So the greater is the stabilization of conjugate acid, more will be the right side equilibrium, that is the product side equilibrium lies, and the stronger will be the base and the smaller will be the pKb value for that base. Now we will study this basicity of amines related to structural effect which influence in the stabilization of various species. The greater is the stabilization of protonated amine, that is the conjugate acid, greater is the basicity of amines. Now here we will study examples, that is for the first effect is influence of plus I effect. So plus I effect is electron positive inductive effect on stabilization of conjugate acid of aliphatic amine and ammonia can be represented, can be shown like this. This ammonia with proton, that is called as ammonium ion. This is primary amine protonated, secondary amine protonated, tertiary amine protonated. So here alkyl groups in ammonium ion, there are no alkyl groups. In primary amine there is a one electron donating alkyl group. In secondary amine there are two electron donating alkyl groups, and in tertiary amine there are three electron donating alkyl groups. So an alkyl group exerts electron releasing or electron donating inductive effect, that is a plus I effect, which stabilizes positive charge on the atom bonded to it. So as we move from conjugate acid of ammonia, that is NH4 plus, to that of tertiary amine, that is R3NH plus, the number of alkyl groups bonded to nitrogen, that goes on increasing steadily, that is from ammonium to tertiary, this number of alkyl groups goes on increasing. The result of this is the stabilization of conjugate acid, and which increases the basic strength of this conjugate acid. Therefore, on the basis of this stabilization of this conjugate acid is, here the tertiary is more than secondary, than primary, than ammonium ion, and on the basis of this, the stabilization, on the basis of stabilization, the expected order of basic strength of amines is tertiary amines are more basic than secondary, than primary, than ammonia. So this is stabilization and the basic strength on the basis of this conjugate acid. The expected order of basic strength on the basis of plus I effect differs from observed order. It is seen that the observed increasing basic strength from ammonia to amine, from primary amine to secondary amine is explained on the basis of stabilization of conjugate acid by plus I effect of increased number of alkyl groups, but the decrease the basic strength of tertiary, that implies the conjugate acid of tertiary amine is less stabilized, even though the plus I effect 3 alkyl groups in R3NH plus are expected to be large, and this is suggestive of existence of another influencing factor in stabilization of conjugate acids of amines. So that is the second effect, that is the influence of solvation. So this factor affects more for the basicity of amines. By this solvation by water on stabilization of conjugate acid of aliphatic amines and ammonia can be represented as here. This is a nitrogen atom, central nitrogen atom bonded with 3 hydrogen. This is ammonia molecule solvated with 4 H2O molecules around it. Then this is a primary amine, that is RNH2, and it is solvated by 3 water molecules. If you compare this solvation for secondary amine and tertiary amine, then here this is R2NH. It is a secondary amine solvated with 2 water molecules. This is R3N. It is a tertiary amine solvated with 1 water molecule. So if we compare this solvation with water molecules, then ammonia require 4 molecules, primary amine require 3 molecules, secondary require 2 molecules, tertiary require only 1 molecule. So the water stabilization, the conjugate acid by hydrogen bonding through hydrogen bonded to nitrogen plus ion. The number of hydrogen atoms bonded to nitrogen plus decreases from 4 in NH4 plus 1 in N3 NH plus. As a result of this, ammonium ion is the best stabilized by solvation, while the stabilization by solvation is very poor in tertiary amine. The third type of effect which explains the basicity, that is the combined influence of plus I effect and the solvation effect. So this conjugate acid in aliphatic amine decides the observed basic strength and pKb value. These two influencing factors operate in opposite direction. First is a solvation. It is more in NH4 plus than primary, than secondary, than tertiary amine. And plus I effect, it is in exactly opposite order. So the net result is, it is ammonia to primary amine to secondary amine, the basic strength increases due to the better stabilization of corresponding conjugate acid. But the tertiary amine is weaker base than the secondary amine because of stabilization of conjugate acid of tertiary amine by solvation is very poor. So remember this reason. Then basicity of aryl amines. We will study now basicity of aromatic amines, that is the aryl amines. From the pKb values, we understand that the aryl amines in general are weaker bases than ammonia and aliphatic amines. The strength of aryl amines is explained in according to Lowry-Bronsted theory by writing the following equilibrium reaction. So consider this reaction. This is aniline, that is phenylamine. When H2O is added, it forms the conjugate acid, that is nitrogen get protonated and OH minus is the side product. Here the both base and the conjugate acid are resonance stabilized, but to the different extent. In aryl amines, the NH2 group is attached directly to aromatic ring, and the lone pair of electrons on nitrogen is conjugated to aromatic ring is less available for the protonation. Hence, aniline is a resonance stabilized by following 5 resonating structures. Here in the first structure, this lone pair of electrons from nitrogen are donated to aromatic ring, and in the second structure this lone pair forms the negative charge at second position, then in fourth position, then in sixth position. Like this, there are 5 resonating structures for this aniline. On the other hand, the anilinium ion obtained by accepting proton does not have lone pair of electrons on nitrogen. Hence, it can be stabilized by only 2 resonance structures and therefore less stabilized than aniline. Here, the structure of this anilinium ion, this double bonds are electron that is moving from one position to other position. So these are the resonance structures for anilinium ion. As a result, this equilibrium shifts toward the left side, and this makes aniline weaker base than the aliphatic amines. And that is about the basicity of aliphatic amines and aromatic amines. Thank you.